Hello, future viewers. Welcome to my lightning talk on fighting and overcoming the complexity limit. Another way you can title this talk is using a verifier-friendly algorithm. The agenda is pretty straightforward. I'm more or less going to go over a chronology of events while pointing out along the way some interesting tidbits. For context, I've been working on a project called microsegmentation. You don't need to know too much about what microsegmentation is, other than that it's more or less an applied form of packet classification, where packet classification is the traditional networking research topic, at least one of them. The problem statement in this case is that we receive packets off the network, and then we want to categorize these packets into user-specified flows. Once we have a flow associated with a packet, we want to take some kind of user-configured action, for example, drop the packet, reroute it, etc., etc. Another important thing to point out is that we are currently on the 5.4 kernel, meaning that it's not too old, but it's also not the newest kernel, so we can't take advantage of the latest upstream kernel features. I'm sure anyone who's worked in depth with BPF before has experienced this kind of pain where you have to be waiting for kernel upgrades to use the latest and greatest features. So here's the first pass at the BPF code I wrote for microseg. There's a lot more code than this, but the loop is where all the complexity is contained, so I've decided to focus on that for this slide and the rest of the slides in this presentation. As you can see, the algorithm is pretty explicit. It's pretty simple. Essentially, we're walking over an array of policies, and then we try to match the packet against each policy. As soon as we find a match, we bail out and return the requested action code. This worked pretty okay as a prototype. It was functional, but as you'll see in the next slide, things started to get a bit hairy once we started adding more features. So at this point, there's a lot more complexity in the body of the loop, as you can tell. It turns out the verifier really does not like control flow in the body of the loop. From what I could gather, every time something like continue was inserted into the body of the loop, the number of states the verifier had to explore would double. So we really quickly hit the complexity limits the verifier imposes, which is 1 million instructions explored. To get around this limit, we had to start spreading out policy processing between multiple tail calls. However, the downside to that on the 5.4 kernel is that you can no longer mix tail calls with BPF to BPF calls, meaning that all the helper functions that you see in this function had to be inlined. What this means is that instead of the match function being verified once per loop iteration, it was being verified 4 times, which had really disastrous impacts on the scalability or the complexity limit. It was painfully obvious by this point that the current implementation would not scale. For example, we could barely get to 256 policies/rules, let alone the deep thousands that we were aiming for. On top of that, overhead, even at 64 rules, where we're matching the 64th rule and the first 63 are just duds, the overhead was way too high. We were dropping network throughput from 12 gigabits a second to 8 gigabits a second, which is pretty much unacceptable. A lot of that had to do with the fact that we're doing 8 rules per tail call, and reparsing the packet for each tail call. So we had to get rid of that somehow as well. Fortunately, there's a large body of theory behind packet classification, which I wasn't aware of until now. So we did some literature review. So it took a good bit of searching, but eventually found this paper that was really relevant to the problems we were having. That's the first bullet point. The premise of the paper is pretty much how to implement IP tables using BPF, along with some pretty nifty techniques that I'll go into the next slide. The second bullet point is a book that I found super helpful. It's called Network Algorithmics, and it contains a lot of really fancy algorithms that are distilled into just a few pages. I've learned a lot of interesting things from just skimming the book when I wake up in the mornings or whatever. So highly recommend that. So both the paper and the book in the previous slide both go into pretty good depth about this algorithm called linear bitvector search. The basic idea, and I'll lay it out pretty briefly here, you can read this slide more in depth if you want, is that we're going to decompose a packet into a bunch of dimensions, and for each dimension we can do a lookup from a map that returns us a bit vector. Once we have like n bit vectors, we can do bitwise arithmetic over all the bit vectors. So for example, if we have bit vector for source IP and a bit vector for dest IP, and you bitwise AND them, the resulting bit vector tells us all the policies that match the source and dest. Once we have this final bit vector, we can do U64 size strides over the final bit vector to identify non-zero U64. What this means is we can basically process 64 policies at once in just a handful of machine instructions, meaning that the fast path is really, really fast. And then you can do this really neat little trick at the end once you have the final U64 and find the first set bit using something called a de Bruijn sequence. So on top of being a pretty elegant algorithm, at least in my opinion, LBVS is verifier friendly because the body of the loop is really tight and there's minimal control flow, as you'll see in the next slide. It's also super cache friendly because we're doing straight line data access. So the hardware prefetcher can prefetch pretty accurately. It's also super CPU friendly because modern CPUs can tear through word-sized logical operations. So all this combined means that we have a really fast algorithm despite the fact that it's a linear algorithm. So here's the third pass and the full rewrite of the BPF portion of microseg. The top half of this code snippet is the Bitvector lookups. It's just 2 of them here. There's multiple, like I mentioned before, 1 for each dimension of the pack that we care about. Once you have all the bit vectors, then you do the linear search portion of the algorithm, and that's the loop that I'm showing here. Pretty much you're doing word size strides over all the bit vectors and doing some kind of arithmetic operations. The logic is kind of convoluted here because a lot of it has to do with our product requirements, but hopefully you get the idea. Cool thing is that when you disassemble this loop body, it's actually not that many instructions because we're just doing some very basic word-sized data accesses and some arithmetic operations. The outcome of such a fancy algorithm is that we have finally reached baseline performance, meaning that when you have microseg on, there's actually no visible performance impact because the bottleneck has presumably moved somewhere else. This algorithm scales to 2,000 plus rules in a single tail call, meaning it's super, super efficient, at least on the verifier front of things. The downside, however, is that it's quite a complicated algorithm, and you have to really understand the algorithm before you can make any code changes. Like, you can't just read the code and figure out what's going on. That's going to be more or less impossible. And that's it. Thanks for watching.